At this recording, I'm sharing my screen. All right. So, confession time. I brought your tests with me all day yesterday. They were just there, but I didn't even open them. I didn't have time. So, good intentions, but you'll get them back on Tuesday. All right. And as soon as I'm done marking, I'll post your grades on Moodle, of course. It's already week 12, and usually there's only 13 weeks in a term. And so for me, week 12 is like, ugh. But we still got a couple more classes, or 4, I guess, after this. And we're going to start with the most fun chapter, regression, which is just finding a line of best fit and using it to predict values, things like that, talking about how do we calculate the line of best fit, how does it work, and so we'll talk about that, and then we'll use the line of best fit, and we'll be on easy street. There is some inference that we could do, although I don't have a pointer on here, but in section 8.4, but it's usually not on the final exam, so I make the final exam. So usually I don't have it on there because other instructors might not have time to get there. And so that would be rude because we do a common final exam. And so maybe we'll just kind of take it easy and settle down, right? Might be fun to see it though. But we're in the home stretch here. All right. Let's see here. Oops, that's not us. Chapter 8. I need to make a copy. So chapter 8 is on regression, which is really just a line of best fit, which will involve definitely a scatter plot, right? Kind of a refresher here, so it's been a while. But if we have a relationship between x and y like this, then maybe I have a relationship that looks like this. Okay. And I can fit a line of best fit. Now, because it's a line, it's going to have the format of y equals mx plus b, right? And so where m is the slope and b is the y-intercept, m is the slope and b is the y-intercept, right, where it crosses the y-axis. Just as a refresher on some terminology as well, on the x-axis, we're going to have the explanatory variable. Explanatory variable. It can also be called the independent variable, but I find that that's not very telling in terms of kind of where it goes on your graph, and so I like to call it the explanatory variable. And this is the response variable y. You only have to keep track of one of those to know where the other one goes, right? And so knowing that the explanatory variable goes on the x-axis, then the response goes on the y-axis. Now the response is going to be response variable is the variable we are interested in terms of maybe we want to predict values of y. So the variable we are interested in and often we use the regression line. So I'm going to stop or kind of wean us off of calling it the line of best fit, and I'm going to start to call it the regression line, but they're the same, so you can link those two. And so often we use the regression line to predict values of y. Okay. Oh yeah, I'm so proud of myself. I changed it so you can see my I guess this is like my stationery, I don't know. But I'm so used to you guys not seeing my pen choices that I might be blocking some of the text. So I'm going to try not to do that, but no promises. So before we can fit the line of best fit or build the regression line, we need to kind of take it way back and talk about some other things first. So we're going to learn to quantify the relationship between two numerical variables, okay? Which means that this scenario, two numerical variables would look like this. Y is numerical and X is numerical. Okay. That's where most of our efforts are going to be focused. Okay. It's also possible to, I don't want to use pink because pink is for important things. How about purple? We can also model a numerical response variable using a categorical explanatory variable. So what that would look like is like this. Y is numerical. And X can be categorical. In both of these situations, Y is numerical, right? So the response has to be numerical. The response variable must be numerical. There are methods. Logistic regression lets you model a categorical variable for Y, but that's beyond the scope of this course. So it is possible, it exists, but not for us. Okay, so like I said, usually we start with a scatter plot, and here's our example. We've got a scatter plot which shows the relationship between the high school graduate rate in all 50 US states and DC and the percent of residents who live below the poverty line, which is an income below $23,050 for a family of 4 in 2012. Obviously, that's probably changed now, but so we have some percentage of the population living below the poverty line. Okay? And so if I give you the scatter plot, right, we've talked about, okay, how do I talk about a scatter plot? I can describe this relationship, right? This relationship, I can talk myself into it being linear. So that's a good place to start. Why is that important? For linear regression, when we're fitting a straight line to this thing, it better look like a straight line. Otherwise, I can't fit a straight line to model the relationship. Yeah. Now, I've got this downward trend, right? And so just as a kind of a refresher on the negative, a negative relationship looks like this. And a positive relationship looks like this, right? They're increasing together or as one is increasing, the other one is decreasing, that's a negative relationship. And as a rule of thumb, if you can kind of see any sort of relationship, it's going to be kind of strong. You can say moderately strong or something like that. But if we can see a relationship, since we can see, I'll say a pattern, right? Drew these kind of outer bounds, and I can detect some sort of relationship there. So right away, I know that it's going to be some version of strong, right? Okay. What's our y value? Our y value here is the percentage in poverty, and so that's your response variable, right? Whatever's on the y-axis. And your x variable is your explanatory variable, which in this case is going to be the percentage of high school grads. How are we going to use this? Well, we're going to say that, okay, in this case, we're going to assume that the percentage of high school grads in a state, right, explains changes in the percentage in poverty. Okay. And so in this case, we could reverse these, right? There's no obvious choice for the response variable or the explanatory variable. And in those situations, I would just give you the scatter plot, and then you'll know, right, from the scatter plot, which one is your response variable and which one is your explanatory variable. Okay. And so that's good. All right. Questions? Comments? Concerns? None. We're going to work kind of backwards, where I give you the regression equation, and then we'll work towards finding how we find it. Okay. And so here, this line, y equals mx plus b, right? Just a general line, y equals mx plus b. What we're going to have is y equals mx plus b is going to turn into y hat is equal to, and I want to use, I think I used, okay, b1s and b0s, b0 plus b1 times x on your formula sheet. I'm skipping the covariance and correlation on your formula sheet. You'll have it, but you won't need it. Okay? And so you'll need just a tiny, tiny little bit of it, but we're not there yet. And so that's kind of exciting. Remember when I first handed out the formula sheet, probably scrolled through or looked at it and thought, oh boy, we'll never get through all of this. I'll never have a handle on all this stuff. Today we're going to talk about the covariance and correlation, but the only one that you're going to need really is this little guy. Everything else is just there for show / completeness. And where I'm looking is here. So the least squares regression line, we are going to use this equation here, or this format. I even tell you, with the slope b1, why is b1 the slope? Because it's attached to the x, right? And y-intercept b0, because it's on its own without an x. Okay. So let's see here. Oops. Where b0 is the y-intercept, and B1 is the slope because it's attached to the x. All right, whatever is attached to the x is the slope. What's the y hat all about? The y hat is the predicted value of y. So in a regression setting, a hat means it's a predicted value. Yeah. And like we said earlier, the reason we build regression lines is to model some behavior, which traditionally means to predict kind of other values of y, unseen values of y. Okay. And so we've seen a hat before with p hat, right? But that was the sample proportion and then later the pooled proportion. And so context will really tell you which one's which, right? But in a regression setting, the y hat is the predicted value of y. We can replace the x's and y's with the variable names if that helps, right? So poverty hat is the predicted percent in poverty. And X is the percentage of high school grads. So the hat is used to signify that this is an estimate, but all add-on or prediction. Estimate makes you think of point estimate, probably, which is true. They're the same. So the prediction is a point estimate, and we would, if we wanted to, be able to build confidence intervals around these predictions. We change them to prediction intervals, and again, it's kind of beyond what we do in this course, but it exists. You can do it. You'd need the standard error, so we don't have that. Getting ahead of myself. How do we use this thing? If we know the high school graduate rate in Georgia is 85.1%, what poverty level does the model predict for this state? And so if we go back to our graph here, 85.1 might be, oh, that's kind of a little bit crooked. Whatever. 85.1 might look something like that. Now, this is kind of my fake line. Obviously, I don't have the real line on there, so I can't draw that by eye or just eyeballing it. But I anticipate that the percentage in poverty might be somewhere between 10 and 12, depending on how good I was at drawing this line of best fit. Right? And so now what we're going to do is we're going to plug in a value of x and find the predicted value of y. And so in terms of units, usually we convert percentages into proportions. But for regression, you just want to match whatever the units are on here on this scale, right, on the scatter plot. And so here I have 80, 85, 90. So I am just going to use 85.1 to match the scale on the scatter plot. So here, use 85.1. Oh, it's all glitchy. To match the scale on the scatter plot. That takes some getting used to because you're so well trained and you're used to converting your percentages into proportions, but now you just want to match whatever the scale is on the scatter plot. Okay, so if we are told that the intercept is 64.78 and the slope is negative 0.62, makes sense that we have a negative slope because we said we had a negative relationship, okay? Times the percentage of high school grads. Once we do our math, now it's really important that we do this multiplication first and then subtract it from 64.78, right? Otherwise, you'll get the wrong number. What's nice about regression is you can always kind of check your work, right? We said, I anticipate that this predicted value should be somewhere between 10 and 12, right? And so now I can take my 12.018 and say, well, that looks reasonable because I was just drawing to some fake line that I drew. So it looks like it would actually be kind of here, right? Kind of fudging the line over a little bit, but nothing crazy. So the predicted percentage in poverty in Georgia is 12.018%. Again, matching the units on the scatter plot. This is the percentage in poverty, and so we can talk about 12.018%. Nice. Let's see. Which one of these do you think might be Georgia? Oops. Let's draw a line. I'll go all the way up here. By my best guesstimate, there's one point that I think could be Georgia. We were told that the percentage of high school grads in Georgia was 85.1. So assuming that I'm kind of correct in my scale here, right, might be this one, but I think it's maybe that one. The difference between the actual percentage in poverty in Georgia versus my predicted percentage in poverty in Georgia is going to be called the residual. So the residual is just the distance between the observed points and the line. Okay? And so the residual is just the leftover, right? The residual is the observed minus the predicted. Observed what and predicted what? Observed value of y minus the predicted value of y. So observed y minus the predicted value of y, which we conveniently have a y hat for. And what notation did I use? Oh, even on your formula sheet. Wow, I'm nice. At the very, very bottom, you have the residual is the observed y minus the predicted y. You can use just y minus y hat. So these residuals, some are going to be large and some of them are going to be small. Now, this is where it gets kind of mind-boggling because how the line is fit, so the line of best fit, our least squares regression line minimizes those residuals. Okay? So the way the line fits, if you add up all your residuals, they will add to 0. Okay? And so the line is fit by minimizing the residuals, technically the residuals squared, but let's just hold off on that. So the sum of the residuals would be 0. One of the ways you can check to make sure that you have the right line is if you are able to calculate the residuals using your line, then if you add up all your residuals and they add to 0, then that's a good thing. Yeah. And so if the residuals are the observed minus the predicted, then let's focus on this little guy maybe. This has an observed y roughly, I don't know, 17 and a half. Ish. I should have picked one that was easier to spot. But if we follow that value of x down, which is why you can't have the observed x minus the predicted x, because it's at the same value of x. They would be the same, right? It has to be. That's how you find the residuals. So now your predicted value of y here is 14-ish. So then my residual from the formula sheet, the residual is the observed y minus the predicted y. So my observed y is roughly 17 and a half minus 14. And so that tells me that this distance here, the residual, is 17.5 minus 14-ish. Should do approximately equals, which is what, 3.5? Math. Okay. So then, if we look at points below the line would have a smaller observed than a predicted. So all the points below the line would have a negative residual. Right? These guys would all have negative residuals, and you can try it. But if you're above the line, then in terms of, if I asked you, okay, at this point, is this an over prediction or an under prediction? It's an under prediction, right? Because the residual is positive, right? Is this, at this point, this residual, this is an over prediction, right? We can see it physically, but also because the residual is negative, right? So you can get a lot of information from the residuals, okay? But it requires that we have the line, okay? And so that's what's kind of tricky, okay? The residuals, you would think that we would use R for the residuals, but R is already in use by the correlation, as we'll see. And so instead we use the error, but that's hard to say. And the residual kind of just reminds you more what it is. And so here, E is the error. But each point in your data set will have some residual, right? And so that's why we have a subscript I here. We have the error for point number I, right? where I can be anything from 1 to n. And so we take the observed y at that point minus the predicted value at that point. And but this is, so I don't use the e. You're welcome to. And on the assignment, I think maybe I use e, but on your formula sheet, it just says residual. So whatever you want to use is fine. But it's just the error. Yeah? And so we can calculate the residuals of all these values or all these data points. Yeah, I wasn't done with that. Okay, parking lot the residuals. We're going to talk about the correlation. The reason why we can't use R for the residual is because R is for the correlation. Now I'm going to come back to the residuals. I was wrong in thinking I wish it was next, but we'll talk about the correlation. That's fine. I suspect we do the correlation for quite a while. So that's why I don't want to scroll around too much. Okay. The correlation is a term that we use kind of in regular speech, right? I say, oh, there's a correlation between these two things. And so we kind of have an understanding of what the correlation is. But for us, the correlation describes the strength. And I'm going to say the direction and strength of a linear association between two variables. So it only applies to a linear relationship. Okay? That doesn't mean you can't calculate it. You'll always be able to calculate it, just like you'll always be able to calculate the mean of a numerical variable. But it only is a good measure of center if you have a normal distribution, for example, right? And so so that's why the correlation is so tricky, because you'll always be able to calculate it. It exists, but it only applies if you have a linear relationship. Okay. The correlation, I'll say here, is denoted by R, lowercase r, or capital R. I know why she used capital R in the textbook, but I was raised on lowercase r, and so I'm having a really hard time. So I use lowercase r. You can use capital R. There's a note on your formula sheet. But let's talk about the correlation, just some key aspects of the correlation. So the correlation takes on values between -1 and 1. So here's the correlation R, which means in the center here, you can have a correlation of 0. Okay. If the correlation is negative, then you have a negative relationship. If the correlation is positive, you have a positive relationship, right? Looking like this, or looking like this. A correlation of 0 means that there's no relationship here. There's nothing going on. Okay, and so here, a correlation of 0 means no relationship. What does that look like in terms of the scatter plot? It would just be a cloud of points, right? And so if you have something that looks like this, let's see if I can here. That would be no relationship. Okay. And so because it doesn't matter where you draw your line of best fit can go like this, can even go like this. There's no telling there's no anchor for the relationship. And so that's when we know that there's no relationship. Yeah? As we move out from a correlation of 0 to +1, a relationship with a correlation of +1 is going to look like this. All your points are exactly on the line, a positive line. And if you have a correlation of -1, then you have a perfectly negative relationship. All these points are on the same line, but a negative line. Most of the time, though, let's see if I can find a lighter color green as I move through these. Let's use kind of a rough guideline of 0.5, or maybe something that looks out here. As we're morphing from no relationship to a perfectly positive relationship, right? That's going to look like this. Just going to tighten up as the correlation is increasing. What color can I do that's lighter than orange? I don't think I can. How about gold? So roughly -0.5. I'll clean that up. Is where I do a little cutoff. And I'll talk more about those cutoffs. But a negative relationship, it's some scatter there. Anything, a correlation between -0.5 and 0.5, I use 0.5 as a rough guideline, is going to be considered weak. You're not really going to be able to detect a pattern when you look at it. Okay, and so for this stretch here, we call this kind of a weak relationship. It can be a weak negative relationship or a weak positive relationship if you have the correlation to tell you, right? But then we get into a strong positive relationship and a strong negative relationship. Right? So as the correlation increases towards 1 in either direction, it gets stronger and stronger and stronger. Okay. There. Knowing that about the correlation, let's see here. Move this over. Which of the following is the best guess for the correlation between the percent in poverty and the percentage of high school grads? So first things first, we can narrow it down, right? I know this is a negative relationship, so right away I can eliminate any positive correlation. As a fact about correlation, it has to be between -1 and 1. So that lets me eliminate -1.5 as well. We already said that, okay, well, I can detect some sort of pattern there. And so that tells me that it is not going to be a correlation of -0.1, because that would be very, very close to 0, and that would just be a cloud, right? But I see a pattern here, and so I'm left with -0.75 as my option. I don't like having that down there, so Ta-da! We did it. Do the same thing for the percentage in poverty and the percentage of female householder, no husband present. It's obviously census data or some sort of government collected data. They only collect boring things. But the correlation here, a little bit trickier, right? It's harder to see a pattern, right? And so I would say, kind of like this. You're allowed to exclude some points, but you want to kind of capture the activity, right? And so here, this looks to me like it's going to be a weak positive linear relationship, right? And so if it's positive, right away I can eliminate some negative correlations. I know it can't be 0.9 because I had a hard time kind of mapping out this this relationship, or at least a pattern. So I'm going to eliminate 0.9, but I also was able to pull out a pattern, so it can't be 0.1, right? And so then I'm going to go for 0.5. Yeah. And so that gives you an idea of what 0.5 kind of looks like, because I use that as my threshold for kind of where you go from a weak to a strong relationship. Obviously, this is kind of moderately strong, something like that. And so we did it. But now you know what a correlation of 0.5 kind of looks like, right? And then anything that is tighter than that is going to have a higher correlation. Move this over here. Which of the following has? Nope. Has the strongest correlation, that is the correlation coefficient closest to plus or minus 1. This is a setup. Why? It's a setup because we know from our correlation facts that it has to be a linear relationship, right? The correlation only describes the strength and direction of a linear relationship. And so here I have a nonlinear relationship. So if I fit a straight line to this, it would probably look something like this, making my correlation pretty small, right? Because none of these points are close to this line, right? They're close here and here, but nowhere else. And so the correlation here would be quite low. And like I said, you can always calculate it, but it only applies if you have a linear relationship. Which means I would rank these number 1, number 2. Hard to say between what this correlation would be and what this correlation would be. I suspect this one is higher than A, but jury's out. But this is the one with the strongest correlation, and it would have a correlation closer to positive 1, not negative 1. Okay. I do want to bring in, so on your formula sheet, I'll erase that briefly. We have all this information. Oops. Couple of things. We are only going to use this version. And so we haven't talked about the covariance, and I suspect that it's introduced later. but S subscript X, Y is called the covariance of X and Y. But I also want to highlight that lowercase r and capital R are used interchangeably. So the correlation, if you use Excel to find the correlation, for example, this is the formula that I would use, which would be the sum of the x's times the y. So in your data set, right, you'd have your x column, your y column, and then you could make a new column where you multiply the two together and then add those up, right? That's the sum of your x, y's. You have your sample size, which is the number of points, right? And then you can find your x bar, which is the average of the x's. You can find your y bar, which is your average of the y's. You can make a new column of x's squared, right? Just take your x's and square them, sum them all up. You can find the average of the x's. In fact, you already have it. You can square it, you can multiply by n, and you can take it away from that sum, and then you can take the square root. Holy moly. Do the same thing for the y's, right? That's a job for Excel. I would say, okay, you found that it has a covariance of this, right? And so then you would use this formula. So the correlation, and like I said, it will talk about it, but the correlation is going to be the covariance, which is SXY, divided by, now this is where the notation becomes important, SX, so the standard deviation of the x's, times SY, which is the standard deviation of the y's. The standard deviation of x times the standard deviation of y. Keep that all in the denominator. Okay. So Sx is the standard deviation of x, and S subscript y is the standard deviation of y. Because in our scatter plot, right, we have two numerical variables, and I can find the mean and the standard deviation of each of those individually. And I can use those if I wanted to calculate the correlation. Or you can just use the correlation function in Excel. That's easier. Fitting a line by least squares regression. Here's where the part that I wanted to jump to when we were talking about residuals. So for our residuals, so we said, okay, the line, it gets kind of backwards because the line minimizes the residuals, but then how do we get the line if we don't have the residuals, right? And so it becomes iterative, but that's not for us to worry about. But we want a line that has small residuals. That's our goal. So the first option, option one, would be to minimize the sum of the magnitude so we can take the absolute value of the residuals. Because like we said, if I add up the residuals, they'll just add to zero. So that's not going to help me, right? Because I'm going to have some positive ones, some negative ones, and they're all going to cancel out. So what we're trying to do is make them positive somehow. An obvious way to make them positive is the absolute value, but then all the distances are weighted the same. Okay? And so we use option two, which is to minimize the sum of the squared residuals. Squaring a negative value makes it positive. Okay. but also squaring a larger value makes it really, really large, right? And so it makes it harder to minimize it. And so if we remember our parabolas, x squared, then if I put in 1 squared is 1, right? 1 squared is 1. But if I move out a distance of 1 to x equals 2, what does that do? 2 squared is 4, right? So moving out a distance in the residuals of 1 unit, right? From 0 to 1, okay, I get a squared residual of 1. But from 1 to 2, now all of a sudden it balloons, and I now have a squared residual of 4. Okay? And so what it does is it kind of amplifies these large distances. Okay? And so here, a residual twice as large as another, so from 1 to 2, for example, is usually more than twice as bad. Okay? Bad in terms of fitting our line. Is that right? Okay, good. It is. Okay. So, just like before, we're going to have our estimates, right? Our point estimates, and they'll have corresponding parameters. Now, traditionally, in regression, the parameters are denoted by betas, capital betas. And so the parameter beta naught is the intercept, and beta 1 is the slope. Okay? This is for the population, right? And so parameters are for the population. Oops. I'll do it here. This is the population line of best fit. We take it way back. We've collected a sample from the population, right? And we spent a lot of work making sure that it's a random sample, so it's representative of the population. And we also understand that the sample is just a subset of our population. So we're going to apply the same techniques, right, where we used inference to say, okay, my sample mean is, I don't know, 40, and is that significantly less than 42, for example, right? So what we are going to do is the same. We're going to take a sample and we're going to fit a line to it, but we understand that if I took a brand new sample, I would get a slightly different line of best fit. And the line of best fit, the population line of best fit that I'm trying to get at, that I will never get to, but I'm trying to estimate, is this beta naught plus beta 1x. For us, we're just going to use our point estimates, right? Our work is going to be in the point estimates. And so on your formula sheet, oops, look at us just plowing through our formula sheet today. Are you ready to introduce the last tidbit? Kind of did it in a weird order, but it's okay. For us, the least squares regression line, we've already seen it. Y hat is b0 plus b1 times x. And I even tell you what the slope is. The slope is b1. All right. And the intercept is b naught. You're going to have to calculate the slope and the intercept, but I'll give you some of these values, right? In fact, I need to give you R some way, right? I need to give you SY, which is the standard deviation of the Y's. We've already seen that in the formula for R. I need to give you the standard deviation of the X's, okay, but we already had that from calculating R. So, okay. Then we need to find the slope first, because then we use the slope that we found to find the intercept. As a fact, kind of a fun fact, your least squares regression line will always pass through X bar, Y bar. So here's an LFF, a little fun fact. Oops. The least squares regression line will always pass through X bar, Y bar at the same time. So we use that fact. You just need the formula, but that's where we got this formula from, right? In order to set up the equation of the line and find the y-intercept, we need to know a point that this slope passes through. And that point is X bar, Y bar. And so then we can rearrange it and say, okay, well then B naught, your intercept, is going to be Y bar, which is the average of the Y's, minus the slope that you found, right, times the average of the X's. Nice. Need to find B1 first, which is kind of counterintuitive the way the formula is written. It makes you want to find B naught first, but then you'll find that you hit a block, and so then you'll go back and you'll find B1. Okay. I'm going to introduce it here. We'll talk about the conditions, but I do want to talk about in a regression question, I will give you the following information. I need to give you X bar, the average of the X's. I need to give you, let's do the X's first, S subscript X, which is the standard deviation of X. I need to give you Y bar, average of the Y's. These are all things, if you're thinking about a spreadsheet, right, I'll use green for Excel. You might have your X's, you might have your Y's, These are all things that you could easily calculate, right, in Excel. On a paper exam, though, I'll have to give it to you. Y bar is the average of Y, of the Y's, and SY is the standard deviation of the Y's. Or I'll just say Y to match. From the formula sheet, let's see if it's still in there. Yeah. I need to give you sy, I need to give you sx, I need to give you y bar, and I need to give you x bar. The only thing I need to give you still is the correlation. I need to give you the correlation. There are 3 ways I can give it to you. There are 3 ways I could give you R. The first one is I just tell you what it is. Right. R equals some number. R is stated, I'll say, in the question. That's nice. What's the other option? I give you the covariance. The covariance, which is SXY, is stated. How would you use that? R is SXY over SX times SY. But from above, I already gave you SX and SY. And so it is just one more component that I would need to give you. That's why it's not that much of a stretch. We haven't seen it yet, but I could give you I'll say not introduced yet, but I could give you R squared is stated. Once we've introduced it, then I'll show you how you would get the correlation from R squared. Okay, fine, I'll tell you now. Spoiler. Capital R squared is just the correlation squared. And so the correlation, R, is the square root of R squared. But when I take the square root, I need to tack on the plus minus, because if I have it squared, then it becomes positive, right? We know that about squares. But then if I have a negative relationship from the scatter plot, then you would need to add that back in. I'll make that clear here. So here. So it's not introduced yet, but there are 3 ways that I could give you the correlation. Once you have that, though, you have all the components to calculate the slope and the intercept, and the math is not terrible. And so that's kind of nice. I've got an example, but it's not for a while. The conditions for the least squares line, there's only 3 of them. The first condition is, of course, linearity. It has to look like a straight line to model it with a straight line. And so here, 1, it has to look like a straight line to model it with a straight line. That's fine. We're going to say modeling. And I mean, we talk about modeling a lot, especially in terms of data analytics and stuff like that. And really, one of the main types of modeling that we do is linear regression, just like we're about to do. And so then it makes you sound really cool when you say, oh, I'm just modeling some stuff, you know, how data is. Nearly normal residuals is going to mean that once I have my line, I need to be able to take my, calculate all my residuals, and they should follow a normal distribution. So once I have my line, calculate the residuals, which we do how? That point of x, right? In your data set, you're going to have xy points. So at that point of x, you can use your line to find the predicted value of y, and then subtract it from the observed value of y, and then you have your residuals. So once I have my line calculate the residuals, they should follow a normal distribution. In fact, they should be centered on 0. They should look like this. Constant variability. In order for my line to be useful, which is really what we're checking here, conditions for my line to be useful slash my predictions being robust, usually is what we say, slash robust slash or reliable, let's say reliable, or reliable predictions, we need to check these conditions. And maybe I'll bump this up just a, wait. Make some room for this. So for my line to be useful or give me reliable predictions, these 3 things have to apply. And so far so good. Of course, it has to look like a line to fit it with a line or model it with a line. My residuals should be centered around 0, right? And the way the line is fit, right? If it's a linear relationship, then they will be normal and centered on 0. The constant variability is the only kind of curveball. If I have a relationship that looks this, and I fit a line of best fit here, this is what we call constant variability. Okay? And so here, right, we've got these kind of bands here, and this is constant variability. So we want to have even scatter all the way around the line. Okay? Versus kind of bulged there. Versus if I have something like this, you would probably say, oh, that doesn't look like constant variability, even if you have kind of no clue about, okay, what does it mean to have constant variability, right? But now, if I show you this, you would probably say, oh, so that's what that looks like, right? Why? Because I can fit a line of best fit here still. Okay. The problem becomes that here, I get this kind of funnel situation. Yeah. up to this point, so between these points, I get reliable predictions. Right? All the points are close to the line, and for this chunk of the line, I have very good predictions, right? My line is doing a really good job of capturing and modeling that relationship. Then we get out here. Now, all of a sudden, I have unreliable predictions. Okay. Because I can plug in a value of X here, and I can get a value of Y down here, or it looks like I could reasonably get a value of Y up here. And so then my line does a really bad job for those values of X. The bummer is, unless we have a way to separate our data, right? Maybe these are two groups being modeled together that shouldn't be, so that can happen. But unless we have a way to split this data, right, we can't use this line to model the relationship because we don't have constant variability. Nice. So this is, of course, non-constant variability. Which means our line of best fit, we should try some other modeling technique. And usually, right, we can try to separate the data. Maybe there's two groups, right? You can model them independently. Okay, so looking at the linearity condition, okay, this here, these scatter plots are the original scatter plots, whereas these are what we call residual plots. Residual plots. Well, we've got the anatomy of a residual plot on the next slide, but these are residual plots. Now, what we use them for is really just to magnify the relationship in the original scatter plot, right? And so, for example, this first one looks good, but the second one, I'm a little bit concerned that maybe this is not a linear relationship. In this course, we would still fit a line to it, and we would kind of say, oh, okay, fair enough. But later, if you continue, you wouldn't fit a straight line to this anymore, right? Because here, for this stretch of X, right down here, we're consistently under predicting. Then we're over predicting for the next stretch of X, and then we're under predicting, and that's bad, right? And so we have this non-linear relationship. That's hard to see in the original scatter plot, but it is kind of magnified when we look at the residual plot. So that's why we use the residual plot. The residual plot magnifies the original scatter plot often. So what does it look like? The residual plot is going to have, so this, okay, why didn't they say it? It's going to have the residuals on the y-axis, and it's going to have the percentage of high school grads, or X, on the x-axis still. So now each of your x's has some residual attached to it, so you can plot those instead as a scatter plot. Now notice the residual plot is centered on 0, okay, which we said, okay, the residuals should follow a normal distribution centered on 0. Good. Oops. where can I write this? The residual plot should be centered on 0. And we should have random scatter around 0. With random scatter around 0. We can plot these two residuals here, right? And they would show up in your residual plot. Okay, but what you're looking for in your residual plot is you're looking for random scatter around 0. Here, I think this is random enough. The concern is kind of this funnel, but to me, in this course, that's good enough. Nearly normal residuals, we already said, you can do a histogram of the residuals. So that's pretty self-explanatory. But the constant variability, the variability of the points has to be roughly constant. And so it's also called, kind of fun, homoscedasticity. Homo meaning the same, scedasticity meaning variability. And so homoscedasticity, kind of fun. I bet you that's been an answer on Jeopardy at some point. I wonder. So you can check it using a histogram or a residual plot. Let's move this over here. What conditions is this linear model obviously violating? I'm going to go with it's obviously violating a linear relationship. But from it violating the linear relationship condition, it also doesn't have constant variability, right? And it would not have normal residuals. And so, but the main one is the linear relationship. What condition is the linear model obviously violating? Linear relationship looks good. And the residuals would probably end up looking normal because they would just all stack, right? Centered on 0, so that still looks good. It's the constant variability that's bad. We have non-constant variability. Good. So what are we actually going to do with these problems? Well, I'm going to get you to find the least squares regression line. Okay. And so here's some information on the percentage in poverty and the percentage of high school grads. I wouldn't be this nice and I wouldn't give you the X and the Y's. This is our first one though, so of course have to. Okay. But I would give you a scatter plot, right? And from the scatter plot, you can pick out which one is the X and which one is the Y, right? So let's start there. This is the X and this is the Y. So pretend you don't have these. That would be your first step, right? Mapping, okay, the percentage of high school grads, that's my X. So the mean of the percentage of high school grads is X bar, right? So I wouldn't tell you this. So that's your first job, right? Mapping the information to the appropriate groups. But like I said, this is our first one. So we have it, but just so you can see it coming. Okay. This one's nice. I give you the correlation. The correlation here is negative 0.75. Notice how she uses the capital R. I would use a lowercase r, it doesn't matter. Now, we're going to find, let's just do it together. Find the least squares regression line. Least squares regression line or regression equation. Okay. From our formula sheet, I'll grab it so you can see it happening. We want to find y hat is b naught plus b1 times x. I give you the values in the order that you're going to calculate them. And so first we're going to find b1, b1, the slope is r times sy over x sx. This is where it becomes really important that you haven't mixed these up. In this case, sy and sx are really close to each other, so it wouldn't make a huge difference, but sometimes the scales on these is way out of whack, and so then your line would be going in the wrong direction. Okay. Or at least have the wrong slope. So that would be bad. So you want to keep track of your sy and sx. There. Let's think about standard deviations. Standard deviations are always positive because they're the spread. You can't have a negative spread, right? And so the way that I can get a negative slope is through the correlation, right? That tells me I have a negative relationship because sy is always positive and sx is always positive. And so how I get that negative on the slope is through the correlation. But from here, I'd say you're on easy street. Negative 0.75 times, as long as you've picked out the right value for y and the right value for x, sorry, I get 3.1 over 3.73. Calculate it. Wait. Try to break my calculator. I find that B1 is 3.1 divided by 3.73 times negative 0.75. I get roughly negative 0.6233243968. I'm going to keep 4 decimal places here. Kind of lose interest, right? Nothing's really happening after the 3, and so you can usually safely kind of chop it off there. And so we're going to let B1 be negative 0.6233, keeping 4 decimal places. I know you guys don't like it because I don't say, give me this many decimal places. Use this many decimal places. And that's because I just follow through with your work anyways. But I do want you to keep, around 4. That's usually safe, all right? Depending on what the value is. If it's a huge value, then knowing 0.6233 is not that valuable. Right, but here I have a very small value, so then lots of decimal places makes more sense. So from here on out, I'm going to use this rounded value of the slope, which is fine, right? Why is that a concern? that's going to give me an imprecise estimate for the y-intercept. But that's okay because we're just doing it by hand. Obviously, software doesn't round any values, right? So we can calculate B0, B naught is y bar minus B1 times x bar. Again, really important that you've identified the right x and the right y and attach the means and the standard deviations to the right thing. But once you have, right, switching these two would make a huge difference. Y bar is 11.35 and x bar is 86.01. So that would make a mess. So you want to have 11.35 minus the slope, which is negative 0.6233, times x bar, which is 86.01. If I do negative 0.6233 times 86.01, I get 11.35 plus, because it's a negative, but a negative being subtracted is addition, and so 53.610033. Doesn't really make sense to keep all those decimal places because I already used a rounded value, but that's okay. Plus 11.35. Oh, I didn't ditch my negative. Plus 53.61. I get 64.960033. Here, I kind of lose interest, and I used a rounded value for the slope already, so I'm going to round this to just 64.96. Keeping 2 decimal places. I'm rounding because we're going to use the slope and the intercept in the follow-up questions, and so then it's nice to not have to use the exact values. But then, therefore, y hat is b naught plus b1 times x, but we just found that b naught, so y hat is 64.96 minus 0.6233 times x. Sometimes people prefer we can replace x and y with the variable names. I'm not too concerned about that. I'm fine with just leaving it as y hat and x, but it means that you have to keep track of which one's which. And so we said y, in this case, is the percentage in poverty, and x is the percentage of high school grads. And so what we could do is we could say the percent poverty, or some version of that hat, is 64.96 minus 0.6233 times the percentage of high school grads. So you can rewrite it that way, because remember, the next part of using this line is, okay, so some state has, I don't know, 80% high school grads, right? What's the predicted percentage in poverty? So then you can see that you would just put in the percentage of high school grads and you would get the percentage in poverty, the predicted percentage in poverty. Okay. We can, so here it just walks you through. She rounds to 2 decimal places. Mean, but we did that. The interpretation of the slope, I always follow it up. So usually on the final exam, it's the first time you're being tested on a regression question. And so I like to kind of lay it out nice and slow for you. And so I'll ask you, find the slope, interpret the slope, find the intercept, interpret the intercept, state the least squares regression line. We've done 3 of those 5 things, right? But we need to have a handle on the interpretation, right? And then I get you to use the line to predict a value, right? As we saw coming. But the interpretation is really important. Let's talk about the general interpretation first. I'll do it up here. The interpretation of the slope, B1. What you're going to do is you're going to remember the interpretation of any slope, but then apply the appropriate variable names and numbers to your slope. The slope is going to look like this. For each unit increase in x, we expect a B1, so a slope unit increase in the predicted value of y. You can rely on the equation, right? This general equation, the slope is this. If I take x from 1 to 2, for example, then the y hat would increase by negative 0.6233. I am always safe to say increase, right? You can increase by a negative number and therefore it is a decrease, but you want to be careful. So I don't want you to get too fancy unless you're super confident, right? A decrease of negative 0.6233 would be an increase of 0.6233. So you don't want to do that double negative thing. And so that's why it's always safe to say increase, because if the slope is negative, then a negative increase is a decrease. And so maybe you have your wits about you and you can handle that. But usually, especially in a final exam, I would be too flustered and I just want something that's always going to work. So that's the interpretation of the slope. Add a page. So in our case, right, for each unit increase in the percentage of high school grads, we expect a negative 0.6233 unit increase in the predicted percentage in poverty. I'll write that out. Each unit increase in percentage of high school grads, expect a negative 0.6233 unit increase or 0.6233 unit decrease if you're so inclined. But like I said, decrease. I always just keep the slope as it is and say it's an increase, and then I don't need to worry about it, right? Because you need to be really careful that you don't tack the negative on there. We expect a negative 0.6233 unit increase in the predicted percentage in poverty. So that's how you would interpret the slope. What about the intercept? Is not. Going back to our general equation here, E naught is y hat when x is 0. And so that's the interpretation. And you can use the formula to kind of talk yourself into it, right? We see y hat is b naught when x is 0. And that is the interpretation. The predicted value of y when x is 0 is b naught. So for our example, and you can rework it because often the sentence structure gets a little bit weird, but if you keep the sentence structure like this, that's totally fine. The predicted value, the predicted, I guess I should say, percentage in poverty when percentage of high school grads is 0 is, what was it, 64.96%. Do I? Introduce it now. I do. Is the intercept meaningful? Is usually a follow-up question that I ask. Now, we know lines keep going from negative infinity to positive infinity, and at some point, it has to cross the y-axis at x equals 0. Whether that gives us valuable information or meaningful information, right, is kind of up to us to interpret. Now, in this case, it's the predicted percentage in poverty when the percentage of high school grads is 0. Do you think that you'll ever have a state where the percentage of high school grads is 0. Probably not, right? There is the flip side. Okay, well, what if we eliminate high schools? Well, there would still be some version of it, right? And people would still be graduating. I just don't see us moving away from that structure. And so here, another clue is that our X's here, the percentage of high school grads, is going from roughly 75 to 95-ish, right? And so X equals 0 would be way out here, right? And so grab this. In this case, right, X is kind of from 75 to 95-ish. So X equals 0 would be way out here. How you're going to answer this question is argue whether X can be 0 or not. I don't really care if you argue for or against. In this case, I think it's pretty obvious that you would say, no, it's not meaningful because there are no states with a 0% high school grad rate. And so, but as long as you center it around X being 0, you can argue for or against, and you can convince me either way. But we need to argue whether X can be 0 or can be 0, or if X equals 0 is meaningful. There are no wrong answers, right? But in this case, I would expect you to kind of argue, no, we see that the percentage of high school grads of 0 isn't on our scatter plot. And so we say, in this case, we say the intercept, the y-intercept, is an extrapolation. You're extrapolating outside the values of X that are in your data. Your line really only fits this stretch of X's. So it is only reliable for that stretch of X's. So these 75-ish to 95. There's some wiggle room, but not a lot. Okay? And so, nice. I think I talked too much. But here, the intercept, so where the regression line intersects the y-axis, and so this is what it would look like, right? But our line is really only useful in this little short range, right? And so we call it an extrapolation. I don't like those ones. We've already talked about this, so I'm going to scroll through here. If we fit our regression line using software, it would look like this. We talked about the interpretation of the slope and the intercept. I just kind of did it. I went rogue. Now, we already know how, but you can use the line to make a prediction, right? Y hat is the predicted value of Y. So once you have your regression line, then you can use it to make a prediction. Extrapolation, we've already seen it, but applying a model estimate to values outside the realm of the original data, which we said was kind of roughly 75 to roughly 95-ish. So the line is really only useful in this kind of short stretch. But lines keep going forever. That's not their fault. There's some examples of extrapolation, but I think I'll pick up there next week. If you have any questions, let me know. Otherwise, have a great weekend.